Hello learners, welcome back. In the previous session we were developing the Excel sheet, right, for the design of our beams, right? Okay, so now in order to do that, so now when I go to this, we have designed till the obtaining the tensile reinforcement both for the positive as well as for the negative side, right? You can see here, so this is the number, you don't have any value here, okay, and this is the number, you will not be having any values here. So these are the reinforcements. So this is all about with respect to the tensile reinforcement required. Now after this, once the tensile reinforcement is obtained, right, so once the tensile reinforcement is obtained, you have to go for the check for the shear, right? So in order to do that, so we are supposed to write so check for the shear, right? So we have to do the check for the shear. So now let us develop the Excel sheet for the check for the shear. The first and the foremost step is you are supposed to know the nominal shear stress. Before you know the nominal shear stress, in order to do that, you should know the nominal shear force, right? So therefore the first is the nominal shear force. So we usually nominal shear force, so we give it in the form of VU, and it will be in kilonewton, right? So nominal shear force. Just let us take the value of nominal shear force as around 2035. Okay, so once the nominal shear stress is obtained, the next step is you will calculate the nominal shear stress, NOMINAL, nominal shear stress. Okay, so we call them as tau u. So here I don't have the symbol for tau, so therefore or let me check that is there any value, any symbol looks like the tau value. So you can see here we have a symbols here, right? Yeah, so I can give almost this value. Okay, so therefore I can write tau u, I can write, right, so which will be in Newton per mm square. So therefore when I want to do that, it is this into, I have to convert it into the Newton, so divided by, so small b, that is the breadth of the beam, that is small b, into the depth of the beam, the effective depth small d, right? So that will give you the value of nominal shear stress tau u in Newton per mm square. So once you get that, then you know what will be the percentage of steel provided, right? Because you can see here that you will get the number of reinforcement required in the positive side, the number of reinforcement required in the negative side, right? So therefore here what you are supposed to do is you consider the number of reinforcement required. Usually sometimes you may get it in some unusual numbers like 5, 4, like that. So usually we will move on to the higher value, correct? So we will move on to the higher value, right? We will move on to the higher value. Therefore the number of reinforcement provided will come. So therefore when it comes to the number of reinforcement provided, we have to calculate the percentage of steel provided. Okay, so that is percentage of steel will be 100 AST by BD. That will give you the percentage of steel provided. So I can get the value of percentage of steel provided, that is I can get the AST here. Okay, I can get the AST here. So once I get the AST of 1 bar, when I multiply by the total number, I will get the capital AST. So into 100 by BD will give you the percentage. Therefore I can give I can write AST AST provided. Okay, it will be in mm square. So therefore I can do that. In order to provide the AST provided, I have to find out the small AST. Therefore what I will do is I will cut here, then I will paste here. Okay, I will write here small AST. Okay, so small AST. So small AST means it is the area of the one bar. Therefore that will also be in mm square. So therefore I can provide, which is equal to 3.142 into, okay, yes, so it will be this into this. Okay, so divided by 4 will give you the AST, small AST, that is area of the one bar. So therefore total AST will be equal to, so it will be this, okay, into the total number of bars that you are going to provide. Okay, the total number of bars that you are going to provide. So that will give you total AST. Okay, I'll just make a small change, it is negative side. Okay, so that is the total number of AST, correct? Okay, so now once I get the small AST, then I can find out percentage of steel provided. Okay, that I can write PT provided, PT provided, so which will be in the percentage itself, you know, it will be in the percentage. So that is nothing but I can write 100 AST divided by B into capital D. So this will be B into, this will be capital D, right? Yes, so this will be capital D. So that will give you the percentage of steel. So once I get the percentage of steel, okay, once I get the percentage of steel, you can see here that the percentage of steel provided. So you have to go to the IS 456. So you have to go to the IS 456. So from the IS 456, so get the permissible shear stress, that is tau C in the Newton per mm square from the table 19 of IS 456. So once you get this, so with the help of this percentage of steel provided and based on the grade of concrete you are going to provide, so permissible shear stress, okay, so that I'm going to write it as the permissible shear stress as, let me copy this symbol. So this tau U, so I can give tau C, right, permissible, okay, permissible, so which will be in Newton per mm square, right? So that value I'll going to get from the table. Okay, I can write it, so table, so I'll write it as almost 1.2 Newton per mm square. Now when I get that value of permissible shear stress, then one more I have to write, it is the maximum shear stress. Okay, so that is again, it is, I can write tau maximum. Okay, so that is also we are going to get it from table only. Okay, so that will be also Newton per mm square. So let me give it as 1.1. right? Now when I find out the permissible shear stress, and when I find out the maximum shear stress, and when I find out the nominal shear stress, in case if my nominal shear stress value is less than the permissible shear stress, then just provide the minimum shear reinforcement. Okay, so I will tell you how to provide the minimum shear reinforcement when we calculate the reinforcements for the each group beam groups. Okay, if my permissible shear stress is more than the nominal shear stress, or if my nominal shear stress is less than the permissible shear stress, okay, I'll just write here my nominal shear stress Okay, you just write it here. Nominal shear stress, it is less than the permissible shear stress. Okay, nominal shear stress less than the permissible shear stress. When my nominal shear stress is less than the permissible shear stress, so then what you are supposed to do, you are supposed to provide minimum shear reinforcement. Okay, you are supposed to provide minimum shear reinforcement. Okay, supposed to provide minimum shear reinforcement when the nominal shear stress is less than the permissible shear stress. In case if your nominal shear stress, okay, if in case your nominal shear stress is, okay, if in case your nominal shear stress, if it is greater than the permissible shear stress, if your nominal shear stress is greater than the permissible shear stress, then you are supposed to design, okay, supposed to design the shear reinforcement. Okay, yes. Now in case if your nominal shear stress, in case if your nominal shear stress is higher than, okay, is higher than the maximum shear stress, it is higher than the maximum shear stress, then you have to redesign the beam. It is not allowed as per IS 456. You have to redesign the beam. Okay, yes. So this is how it is. You are supposed to redesign the beam, right? Okay, so now let us assume that my nominal shear stress is more than the permissible shear stress, so therefore I have to design it. So therefore when I go for the design, you have to calculate the shear strength of the concrete, that is VUC, the first one. Okay, so that is shear strength of the concrete, which is given by VUC. Okay, so the shear strength of the concrete which will be given by VUC, it will be in kilonewton, right? So how will you get the shear strength of the concrete? It is the tau c, okay, that is your permissible shear stress into B into capital D. Okay, yes. So that is nothing but I can write that permissible shear stress into, so your B into your capital D, right? So that will give you this in, it will give you the value in Newton, divide by 1000, so that will give you the value in kilonewton. So once you get the shear strength VUC, the next step is the shear to be carried by the steel VUS. Okay, so the next step is the shear to be carried by concrete, that is VUC. Okay, sorry, VUS, to be carried by the steel. Okay, it is VUS, so that will be also in kilonewton, right? So for that, what you are supposed to do, VU already you know, you substitute, you subtract VUC, that will give you VU. So that means it is equal to VU, you have already calculated here. Okay, so minus this VUC, that will give you this. So let us keep it as 200. Okay, so that will give you VUC, right? Okay, so once you do that, VU minus VUC, so then you are supposed to calculate the spacing of the stirrups. So before you do the spacing of stirrups, you have to supposed to assume the diameter of the reinforcement that you use for the stirrups, and you find out the area. Okay, you are supposed to find out that area of that stirrup, and while doing that you should be in a position to choose whether I am choosing two-legged stirrup or one-leg stirrup. So now let us assume that all the stirrups will be of the two-legged stirrup. So therefore I am supposed to write diameter of the reinforcement for stirrups. Okay, so the diameter for the stirrups, right? Yes, so that will be in mm. That will be in mm. So let me take it as 10. So therefore area area of one stirrup, area of the one stirrup. Okay, so that will be in mm square. Okay, so that will be in mm square. So that will be equal to 3.142 into 10 into 10 by 4. That will give you the, and that has to be multiplied by 2 here, because I already told that it is a two-legged stirrup, right? So therefore it will be the area of the one stirrup. So once you get that, you get the spacing of the stirrup SV. Okay, so spacing of the stirrups SV, it will be in mm. So it will be equal to 0.87. Okay, I can make it 0.87 into, you have already chosen f of y, okay, into f of y into ASV. ASV is nothing but this one into small d. Okay, small d. So divided by VUS. Okay, so VUS, so it will be like this, so into 1000. Okay, yeah, so I didn't close the blocket. Yes, so now, yes, so that will give you the spacing. 1 second. Yeah, yes, so that will give you the spacing. So anyhow the spacing is not proper because the values that I have taken is not correct, right? So that will give you the final spacing of the stirrups. So your spacing of the stirrups as per IS 456 2000 should not be more than 300 mm or should not be more than 0.75 times D, right? So it should not be more than, okay, so it should not be it should not be, or I can, yeah, it should not be greater than, it should not be greater than the first one, it should not be greater than the first one will be 300 mm, or the second one will be 0.75, into D, small d. Okay, 0.75 into small d, right? 1 second. 0.75 into small t, right? So it should not be the greater than of these two value. Okay, for example, if you are getting around 500 mm, then check out this, out of these two whichever is smaller, 300 mm, that has to be provided. Okay, so in this way you are supposed to provide the shear reinforcements. So in the next class, so let us take up the beam groups and let us start giving the values, and let us get the positive reinforcement, negative reinforcement, and then finally the shear reinforcements. Okay, thank you learners.